Good day, everyone. I am Argel Largado from the Institute of Food Science and Technology, University of the Philippines, Los Baños. On behalf of our team, I will be presenting our research on the physicochemical and antioxidant properties of cocoa bean shell waste from chocolate processing. This study is part of a bigger research on the development of functional food products and ingredients from CBS waste. As a background, this project was started to address the long-standing concern of the chocolate industry regarding the waste generated during processing. Food scientists from our institute collaborated with Malagos AgriVentures Corporation, or MAV, the makers of internationally recognized Malagos chocolate. Based on the data obtained by MAV, about 18 to 35% of the cacao bean weight goes into waste after roasting. This is depending on the type of the equipment used and processing applied, which translates to roughly around 1 to 2 million pesos annually. So the objectives of the study is to be able to utilize the cocoa bean shell byproducts. It is important to investigate its inherent properties first. Hence, the objective of this study was to determine the physicochemical and antioxidant properties of CBS. So data from literature have presented the potential of CBS to be sources of antioxidants because of its high phenolic content. So this is the overview of our methodology. First, we prepared the samples by grinding and passing through sieve number 20. Then we analyzed for its heavy metals and microbiological properties to check if the product is safe for consumption. After that, we proceeded with the determination of its physicochemical properties and proximate composition. Lastly, we checked for the CBS's bioactive components and antioxidant activity. So for the heavy metals, samples were sent to SGS for analysis. Samples were analyzed using acid digestion and atomic absorption spectroscopy. So the microbiological analysis of the samples was conducted using the conventional plate count method based on the bacteriological analytical manual. So the aerobic plate count was determined using plate count agar. The coliform count was enumerated using the violet red bile agar. And the yeast and mold count was determined using potato dextrose agar, acidified with 10% tartaric acid. So for physicochemical, water activity was determined using the Novacina water activity meter. And the color profile was determined using the Minolta Konica chromometer. For the proximate composition, we conducted it according to the AOAC 1990. Moisture was determined by oven drying. Crude protein content was determined by Keldal method. Crude fat was analyzed using the Soxhlet method. And crude fiber was analyzed by sequential digestion with acid and base. For ash, pre-dried samples from the moisture determination was used and ignited using a muffle furnace. Amount of NFEs was calculated by difference. So for the analysis of bioactive compounds, we started with the preparation of the extraction solvent. We conducted it according to Laurari et al. 1997. So the mixture was methanol, water, acetic acid in 50:50:1 volume ratio. So 1 gram of sample was placed in that mixture, and then we placed the mixture in a shaker for 1 hour at room temperature, after which we subjected it to centrifugation for 15 minutes. And the supernatant was collected and stored at negative 20 degrees Celsius. After extraction, the total flavonoid, total anthocyanin, total phenolics, and condensed tannin contents were quantified using spectroscopic methods. The total flavonoid content was evaluated using the flavonoid aluminum chloride complexation method according to Fatahi et al. 2014. The total anthocyanin content was analyzed using the pH differential method based on AOAC method 2005.02. And condensed tannins content was determined according to Medini et al. 2014 using the vanillin HCl method. And the total phenolic content was determined according to ISO 14502-1 with minor modifications using the Follin-Shokal 2 method. For the antioxidant properties of CBS, ABTS scavenging activity and FRAP and DPPH scavenging activity were determined. FRAP and ABTS scavenging activity were carried out according to Castillo Israel et al. 2020 and Tomasina et al. 2012. And the DPPH scavenging activity was conducted according to Marinova and Bachbarov 2011 with minor modifications. So let's proceed with the results and discussion. For the heavy metal content, results of the CBS waste data was evaluated based on the standards for fruiting vegetables, fruits, commodity containing cocoa solids, indicated on the General Standard for Contaminants and Toxins in Food and Feed, which is the CXS 193-1995, Revision 2019. The results of the arsenic, mercury, lead, and cadmium was within the acceptable level based on the standard. For the microbiological quality of CBS, Table 2 shows the results of the total plate, coliform, and yeast and mold counts. These results were within the acceptable level based on the standards for cocoa powder indicated on the revised guidelines for the assessment of microbiological quality of processed foods, which is the FDA Circular Number 2013-010. Next is the proximate composition. Table 3 shows the proximate composition and physicochemical properties of CBS. The CBS that we collected from MAV Corporation has a moisture content of 6.21%, ash content of 10.74%, crude protein content of 21.67%, crude fiber content of 7.75%, crude fat content of 9.54%, and NFE of 34.55%. It is interesting to note that CBS has high ash, protein, and fiber contents. CBS also has a low water activity of 0.37. For the color profile, L values indicate CBS as a slight dark color, while the positive A and B values indicate a slight shift to red and yellow respectively. So Table 4 shows the results obtained for the total phenolics content, total anthocyanin content, total flavonoids content, and condensed tannins content of CBS. It can be observed that anthocyanins were not detected. However, CBS contains high amount of phenolics, flavonoids, and condensed tannins. Moreover, TPC, TFC, and CTC values were similar to the data reported by Rojo Poveda et al. 2020 on their study of nutritional properties and biofunctional potential of cocoa bean shells. Next is Table 5 shows the antioxidant properties of CBS. Data gathered shows that CBS exhibits antioxidant properties based in the different assays employed, which is the DPPH, FRAP, and ABTS. Moreover, when compared with other indigenous fruits in the Philippines, CBS shows great potential to be a source of health-promoting bioactive compounds. So based on all the data gathered from this study, it can be concluded that the cocoa bean shell, a processing byproduct of the chocolate industry, contain bioactive compounds and exhibit antioxidant activity. So impact of the study is CBS could be a valuable ingredient for innovation which could be used as a cocoa substitute. Additionally, cocoa farmers will benefit economically by reducing costs for disposal of CBS waste materials, and also by converting it into functional ingredients. It could add value to other products, and we could create premium products which is globally competitive in the market. Lastly, the valorization of processing byproducts is becoming a global trend which could impact our environment greatly. So, before I end my presentation, let me acknowledge and thank the DOST Cradle program for funding this research. Thank you also to our industry collaborator, Malagos AgriVentures Corporation, for this partnership. And most importantly, thank you to the Coco Loca project team of researchers and students in the Institute of Food Science and Technology who are working tirelessly for this research. So here are my references. Thank you for your attention. I would like to invite you to visit and like our Facebook page, UPLB CAF's Institute of Food Science and Technology. Thank you.